Hello everyone, welcome to this talk on decoding multivariate multiplicity codes on product sets. I am Siddharth Bhandaria, a graduate student at TIFR Mumbai, and this is joint work with Prahlad, who is again at TIFR Mumbai, our next door neighbor Mrinal at IIT Mumbai, and Madhu at Harvard. This talk is going to be divided into three parts. First, I'll give you a sales pitch of our result. Then we'll take a deeper dive into the parameters of our result. And lastly, we will look at some proof ideas. So now let's understand the setup and what our result is about. Here's a basic fact about polynomials that we all know. That is, a low degree polynomial cannot have too many zeros. That is, if a polynomial has degree at most d, it can at most have d zeros. It can't touch the x-axis too often. Here is a consequence of this fact which is really helpful. If we are given two polynomials p and q which are not identical and low degree, and we consider their evaluations over a set S. So we evaluate these polynomials on each point in S. Then we can say that the number of points where P and Q disagree is rather large. In particular, it is larger than n minus d. This is simply because if we look at the polynomial P minus Q, it can only have d zeros. So it has n minus d non-zeros, and every non-zero is a point of disagreement. Hence the distance between P and Q, where by distance I mean the points of disagreement, that is fairly large, and it is given by this expression over here. We can generalize this basic fact that we just saw in two ways. One is via multiplicity and one is via dimension. So what do I mean by multiplicity? That is, I want to be sensitive to roots of a particular type. You see, this root here is actually a root of high multiplicity as compared to this root, because here the polynomial px just touches the x-axis. So not only is p 0 but even its derivative, whereas here only p is 0. And the other way we will generalize this is in terms of dimension. That is, instead of considering univariate polynomials, we will consider a bivariate polynomial which we will evaluate over a grid, and we will count at how many points this polynomial is 0 while taking into regards its multiplicity. And as it turns out, we get a very nice lemma which generalizes our previous result both in multiplicity and dimension. So let's consider a k-variate polynomial p of total degree at most d, and let's also consider a set of evaluation points of size n, which is a subset of f. Then we say that p vanishes at a point a in this grid s to the k. Since p is a k-variate polynomial, it will take a k-dimensional point to evaluate itself at. It vanishes at a with multiplicity m if not only does p vanish at a, but also all the k partial derivatives of p of order 1 vanish at a. If all the k choose 2 partial derivatives of p of order 2 vanish at a, and so on and so forth for all of the m minus 1th order derivatives of p. And the amazing thing is that the degree roots mantra is still applicable here. A non-zero k-variate polynomial of degree at most d cannot have too many roots of high multiplicity. That is, if you count the roots of multiplicity m, then the number of roots can only be d by m times n to the k minus 1. If you compare it to the result we had for k equal to 1 and m equal to 1, you will see that it's the same thing, because you will get d by 1 into n to the 0, which is again d, which is what we had previously. So it is saying you basically take whatever you have for multiplicity 1 and you just divide by m if you seek a multiplicity m. And if you translate this to what is the distance between two polynomials p and q which are low degree and not identical, it turns out that by a similar argument, this distance is n to the k into 1 minus d by mn. So you can see that the fractional distance, it really doesn't seem to involve the dimension k. And what has happened is that the distance, as m increases, the distance between p and q goes up. So this will be an important factor to remember. So what we've just studied leads to a fundamental algorithmic question. Suppose I give you a subset S of f of size exactly n, and I give you an arbitrary function from s to the k to f to the t. For the moment, assume that k is 1 and t is 1. And I ask you how many polynomials p are there. Since k is 1, I am just asking you for univariate polynomials at the moment of total degree at most d, which are close to r. Now, what does that mean? So r can be thought of as a long vector of length n, and at each point you are given a field value. Now I will take the polynomial p and do the same. I will look at the n points in S and just evaluate the polynomial p on those locations. And between these two vectors, the distance needs to be small. How small? It should be in fact smaller than the minimum distance between any two non-identical low degree polynomials p and q, and times a half. Well, it should be clear that the number of such polynomials or the number of such p's which are so close to r can be at most 1. For instance, if p is close to r and q also happens to say that I am close to r, and both are less than half the minimum distance close to r, then the minimum distance between p and q will be smaller than the minimum distance, which is an absurdity. So combinatorially, we know that the answer can be at most 1. And now comes the really interesting question. Can you do this algorithmically? Given a set S and the function R, can you find the closed polynomial P efficiently? This is a super interesting and a classically studied question. If P and R agree everywhere, this is what we would call polynomial interpolation, which we know how to do. The challenge here is P and R don't necessarily agree everywhere. They have some error and some noise. So this is polynomial interpolation in the presence of noise. And now I will like to highlight the role of K and T, which is the generalization that we consider in our paper. So what happens now is that let's suppose that K here, instead of taking 1 and T is 1, let's say K is 1 and T is 2. So, or T is 3. So what is really happening is that each point, so R is actually a word which is now being decorated on an n cross n grid, and at each point in the grid you are being given 3 values. So, and now you are looking for a polynomial p, which you will again evaluate over the grid n cross n grid. Pardon me for the square versus rectangle aspect ratio. And what you will compare with over here is the evaluation at a point p of a, the x derivative and the y derivative. So you will look at these 3 tuple of values at a, and if they agree, you will count that as an agreement. Even if they disagree at one coordinate, you will count it as a disagreement, and you will put that as the distance between p and r. And you will ask the same question. Notice that combinatorially nothing changes. This is a simple argument. It will still say that there is at most one p which is so close to r. But what has happened is that now we are asking you to tolerate more noise, because remember the distance between p and q with multiplicities goes up as the multiplicity goes up. That is what makes the problem challenging and interesting. And now I will compare our work with what was known earlier. So the classical setting here is the k equal to 1, m equal to 1 setting. So you are given a univariate polynomial and its evaluations, and you want to do noisy interpolation. This is also commonly known as the Reed-Solomon family of codes, and turns out efficient algorithms for doing noise interpolation were known from the 60s, even before the conception of the class P itself. So there was the algorithm due to Peterson, there is the shift register algorithm due to Berlekamp-Macy, and then there is the Berlekamp-Welch style polynomial decoding. There are 2 ways to generalize this. One is the generalization of multiplicity. So you look at univariate polynomials, but you ask for high multiplicity at each point, and you want to do noisy interpolation. This line of work was extended by Koparthi and Guruswamy Wang in a result which does more than unique decoding, and I'll get to that later. The other style of generalization is that you increase the dimension. That is, you ask for bivariate or trivariate polynomials which are noisy and you want to interpolate. So in that line of work, there is a beautiful result due to Kim-Koparty, which can handle the case when k is larger than 1 but m is equal to 1, and it uses a Forney style decoding of concatenated codes idea. What our work does is it tries to sort of generalize both together. So we extend the number of variables we are allowing, and we also work with high multiplicity. In fact, we will work with multiplicities pretty far away from 1. This is not a very accurate representation, so please don't take this slide to the bank because there are some catches here. So as a bonus first, let me tell you that we get list decoding as well. It's okay if we do not know at the moment what is list decoding, I'll get to it. The catch here is that we can only work with large multiplicities. We are unable to work with multiplicity say 2 or 3. And we can only work when the underlying field that we are working with has large characteristic. So this is a limitation even in the previous works. But we will see when we get to it. Now I will like to present our result. So this is like an informal statement presented formally. So what we actually deliver is an algorithm for list decoding k-variate multiplicity codes over grids. In other words, we are able to do noisy interpolation for k-variate multiplicity codes, and not only are we able to tolerate noise which looks like half times the minimum distance, we are actually able to tolerate much more noise. You can take any epsilon here. However, we need a few things. We need the underlying field that we are working over to be large, and we need the multiplicity of the code to be large enough as a function of k and epsilon. Now, why is it being called list decoding? It is being called list decoding because you see, when epsilon was half, you had a combinatorial argument saying that there is only one p which works. When epsilon becomes closer to 0, there might be many p's which work. There is no longer the combinatorial argument that only one p works. But we have an efficient way of listing out all these p's, which in turn means that the number of such p's itself is small, which was not even clear combinatorially. And our result is tight in the sense that when you set epsilon equal to 0, that is, you ask us to tolerate as many errors as the distance between p and q, this list size, number of candidate p's, will just shoot off. So there is no hope of getting a polytime algorithm. This talk is going to be divided into 3 parts. First, I'll give you a sales pitch of our result. Then we'll take a deeper dive into the parameters of our result. And lastly, we will look at some proof ideas. Now, I will take a deeper dive into our results. And quite frankly, this is going to be more like an Olympic race. I'm going to really rush through this part. So let's do a flash recap of what we know. We have handled the case of high multiplicity, and we have understood what it means for a polynomial to vanish at a point A with multiplicity m. In case of univariate polynomials, that just means all its m-1 derivatives along with itself, this entire vector has to vanish at A. And we realize that the degree 0 mantra works here, just that if you ask for roots of multiplicity m, the number scales down by a factor of m. We also understood the high dimensional variant of our degree 0 mantra. That is, if we look at a non-zero polynomial of total degree d evaluated over a grid s to the k, then the number of zeros of such a polynomial fractionally doesn't really depend on k. And this is just saying that low degree polynomials do not vanish very often on a large grid. This is a multivariate generalization of what we saw. Then we saw what it means for a polynomial to vanish with high multiplicity when it is a multivariate polynomial. So it precisely means that all its partial derivatives of order less than m vanish. So del p by del xe just refers to this partial derivative. And for k equal to 1, this is precisely the univariate notion. And we saw a corresponding lemma, which is called the multiplicity Schwarz-Zippel lemma, which governs the number of zeros that can happen for this multivariate polynomial. So this lemma is due to Dwyer, Koparty, Saraf, and Suden, and it says that even in the multivariate setting, if you ask for multiplicity m zeros, they can only be as many as d by m fractionally. So it just takes the univariate result and scales it by 1 over m. So a low degree polynomial does not vanish with high multiplicity very often over a large enough grid. And then we ask the algorithmic question that we are given an arbitrary function r on the grid, and at each point we are given the supposed evaluation of p, its derivatives in various directions of order up to m minus 1. And we wanted to do noisy interpolation. So there were some of these locations where maybe some bit of information got corrupted, but we want to find all polynomials p which agree a lot with r. So this is just a restatement of the fact that delta pr is less than n to the k by 2 times 1 minus d by mn. And we combinatorially saw that at most one polynomial can do this. We were interested in the natural algorithmic question. Can we do this efficiently? Right? We can generalize this question even further. Till now, we've been asking just the following question. That is, we have a word r, and we would like to find the polynomial p which is closest to r, which is within distance half of the distance between p and q, where q is the closest code word to p. Maybe let's say q resides somewhere over here. But we can always generalize this. We can say, okay, maybe you find me not only p, but any code word which is close to r. And by close now, we mean which is within distance 3/4 of this, or in general 1 minus epsilon. And as you can see, that no longer is that combinatorial argument of uniqueness of p valid. So naturally we have to produce a list of all such p's, and that is how we get the name list decoding. Pardon this p prime, this should have been q. So now I'll present a detailed comparison with the prior work. So let's first look at the setting of k being 1 and m being arbitrary. So this is just a univariate polynomial along with various of its derivatives being provided, and we are working over an arbitrary set of evaluation points s. This question was answered by Koparty and Guruswamy Wang, where they show how to list decode such polynomials up to distance. That is, not only are they able to find p's with this guarantee, that is close enough to r, but they are able to make this half into any 1 minus epsilon that we desire. However, for that task they require m to be large, but nonetheless the unique decoding task is solved. Now let's generalize both of them, which is the kind of problems we are tackling in this paper, which is k being greater than 1 and m being greater than equal to 1. And further, let's impose that S has an algebraically nice structure, that is, it is a subspace or a subfield. Then we do know how to do something. We are able to list decode up to the Johnson radius. What that means is that it's somewhere between half and 1 that we are able to decode. That is, this half can be replaced by some number between half and 1. So in particular, unique decoding is done. This is done via reduction to the univariate case using the Pelikan-Wu argument. However, when we return back to the regime of working with an arbitrary set of evaluation points, things become tougher. So the case of m being 1 and k being greater than 1, that is famously known as the Reed-Muller codes, was solved beautifully by Kim and Koparty using a Forney style decoding of concatenated codes. However, if you extend this just by a little bit, that is m being greater than 1 and k being greater than 1, with the set of evaluation points s not holding any structure, even unique decoding isn't known. So this is the open problem I would like to leave you guys with. Even for the specific setting of k being 2, that is bivariate polynomials with their first order derivatives also provided. In this paper, we explore some territory of this region of k being greater than 1 and m being greater than 1 with arbitrary set of evaluation points s. In particular, we explore this region where the multiplicities are fairly large. Here we are able to list decode all the way up to distance. So we exactly do what Koparthi and Goswami-Wang did in the case of k equal to 1. However, there is a catch here. We require large multiplicities firstly, and we require the fields to have sufficiently large characteristics. This is also a feature of the univariate algorithms of Koparthi and Goswami-Wang. And now I will flash our result once more so that it will make more sense, hopefully. So we are able to list decode k-variate multiplicity codes over arbitrary grids. So this code is just a polynomial with the requirement of f being a field of large characteristic, the multiplicity being large, and this is tight. That is, the moment you set epsilon to be 0, there will be too many candidate p's to output and you can't do that efficiently. This talk is going to be divided into 3 parts. First, I'll give you a sales pitch of our result. Then we'll take a deeper dive into the parameters of our result. And lastly, we will look at some proof ideas. Now I would like to provide you with a few proof ideas. So this proof is an application of the polynomial method to coding theory, and it broadly follows the outline of works done prior to this work, and it is most closely influenced by the linear algebraic decoding argument of Goswami and Wang. So let's look at what the Goswami-Wang argument was for the univariate case. So let's recall the setup again. So we are given a univariate polynomial here with its evaluation and its derivative, since m is 2, and the set of evaluation points happen to be an arbitrary set in f of size n. So we can think of the received word r as a 3-tuple ai, bi and ci, where what we are interpreting it to be is that the polynomial p which is close to r at ai will evaluate to bi, and at ai its derivative will evaluate to ci. But this is not the case. We don't have that. This would have been the case had it been noiseless interpolation. But since we are doing noisy interpolation, we need to find all polynomials p which are close to r. That is our setting. And the closeness, we by now know what that means. So let's now understand what the Goswami-Wang approach was to solve this question. The first step is a step which is commonly used in polynomial based decoding algorithms. That is, you find a non-zero low degree polynomial q which explains the data. What do I mean by that? I mean that when you look at the word r that you have, and when you plug in ai, bi, ci for all I in n, this polynomial vanishes. So in that sense it explains the data. And this is just a plain linear algebraic argument. You need enough variables so that you find a non-zero polynomial which does that. The second step is to argue that if p is close enough to r, that is delta pr is tiny, let's say even this, then if I plug in p and p prime instead of y1 and y2, this polynomial is identically 0. This usually requires showing that this polynomial has a lot of roots and its degree is low, hence it has to be 0. This is the Schwarz-Zippel lemma that we saw previously. And the third step is to then use this identity. Since this is a polynomial identity, mind you, this is identically 0. We can try to guess the coefficients of p and p prime because we get several constraints on them. And In fact, it is possible to show that the solutions to such an equation, they lie in a low dimensional affine space, and now you can either iterate over the affine space or you can do further refinements, but that is the broad outline. So now let's look at the multivariate extension of what we just saw. And mind you, the description I gave in the previous slide is not an accurate description of what Kuluswami-Wang is, but it's a moral description of what Kuluswami-Wang is. So let's recall our setup here. We are trying to work with multivariate polynomials with their derivatives. So let's say that we have this word R evaluated on S cross S, where at each point A, we are given three values which are supposedly P at A, the derivative of P in the two different directions at A. So we will think of AI as the point where we are evaluating, where AI itself is a two tuple, and then BI, CI, DI represent the various derivatives and the value of P itself, had things been noiseless. However, we again want to do noisy interpolation. So we will try to copy what Kuluswami-Wang did previously. For that, we need the first step to be explaining the data. Now here there is a very natural way. You say, okay, now I have three data points that are given at a particular x1, x2. So I will write a polynomial of this form and I will make it vanish on all such points. This is fairly easy. The linear algebra still goes through. The second point is, okay, I need to show that if P and R are close enough, this polynomial Q is identically 0. That is, its degree is low and there are enough roots, so it has to be 0. And this works out. This again works out. We have strengthened Schwarzschild lemmas which can take care of it. What doesn't work out is that it's not clear how to recover the polynomial P by just knowing that this polynomial is identically 0, that from the belly of this beast it's not clear how to recover P. So what we do is that we try a less natural way to extend Kuluswami-Wang. So the crux here is to consider Z1 and Z2, two new formal variables, which will help us tie the derivative data together. What do I mean by that? We will still look for a low degree polynomial which will explain the data. But as you can see, this polynomial has lost y3 which was there previously, and there is a reason for it. Now we will let y1 play the role of PA which it was playing previously, but y2, rather than just being a vanilla derivative in the x or the y direction, has now become a formal combination in the z1 z2 variables using the derivative data. And now we will look for a polynomial Q which explains the data in this strong sense. Of course, this will force Q to get coefficients from the field Fz, but that's okay. We can live with that, and this is not going to make us inefficient. The second step, so the first step goes through with linear algebra. Again, it's just counting variables and equations. The second step also goes through the Schwarzschild lemma, still rescues us, and we can say that if P is close enough, when we substitute P into the polynomial Q, we will get a zero polynomial. That is, this polynomial is identically 0. The advantage of doing all this is the third step. Here we get a differential equation which we know how to solve. In fact, we know how to solve many more general equations of this kind, and this was already present in the work of Guo, Kumar, Sapirishi and Solomon. And with that, I will leave you with this open problem which I find fascinating, that is just unique decoding for bivariate polynomials with their first order derivatives provided. Thank you for attending the talk.